Hello. Today we're going to be talking about thorium reactors, pinnacle of modern science that's actually been around for about 60 years. However, society hasn't gotten around to actually implementing them commercially or industrially. I think that society could greatly benefit from the implementation of these engineering marvels, and that it could solve a lot of our current problems. So, the main reasons that nuclear power hasn't really been able to fix our energy crisis or the climate change, it really comes down to five sections here. One of them is the fact that nuclear power plants create a lot of radioactive waste. And this waste is often portrayed in movies, and it's actually not that far off. Although it doesn't mutate beings into zombies, it does last for tens of thousands of years, and it'll kill anybody who goes relatively close to it. So it is a giant problem, and the amount of nuclear waste that gets created only will increase if we try to build more nuclear power plants. The second section is the fact that nuclear power plants are capable of manufacturing weapons-grade plutonium, which only expedites the nuclear proliferation, making it easier for countries like Iran to make nuclear weapons. So if we continue to invest time in improving uranium-powered nuclear reactors, we could be letting countries get their hands on weapons-grade materials to end the world. Third is that nuclear power plants, although they kind of get a bad rap about it unfairly, they do tend to blow up randomly. The main problem that normally causes something to explode in a nuclear reactor is the fact that everything is at extremely high pressure. Because you have to use water in nuclear reactors, that water is going to be at a high temperature and expand a lot. So if anything goes wrong, you're going to have a lot of pressure, a lot of radiation, and a whole lot of boom. So, generally speaking, they're not the safest power plants to be around, but we have a solution for this, which I'll talk about later. Another problem that's plaguing nuclear power is the fact that you need to refuel the reactors about every half a year. And this takes a lot of time because to start up a nuclear reactor isn't just a flip of a switch. It can take like about a week to fully get a reactor up and running. And that's a lot of time given that you need to do that about twice a year, so it really slows down the process. And I guess I kind of already incorporated number 5 with number 3, but let's just go on. Now, this is how thorium can be the solution. Not only does it produce significantly less waste, but that waste that it creates is less toxic than that is created by uranium-powered reactors. Secondly, it's much harder to get weapons-grade plutonium out of a thorium reactor due to the fact that thorium is incapable of producing plutonium. Thirdly, thorium reactors allow the entire system to be a liquid and not have any gaseous water running around the system that could cause a lot of issues, which tend to make things explode. Number 4 is that you can run these essentially constantly. Since we'll get to the specifics later, but you can refuel them without stopping the reactor, which is a major benefit both financially and also it just makes it a more effective plant that has a constant runtime. So before we get into all this specifics here, I guess it's first important to understand what even is a nuclear reactor. Essentially what's going on here is you take a piece of uranium, in this case uranium-235, and you blast a neutron at it. And that uranium atom doesn't really like that. It becomes unstable, And eventually it undergoes a process called fission, in which it splits into two different elements, notably krypton and barium. And this process actually releases 3 additional neutrons, as you can see in the center of the screen. And these neutrons are able to start more fission in other uranium atoms. Given that it only took 1 neutron to start the reaction, 3 can triple the amount of fissions that are occurring. So there is essentially an exponential increase in the amount of energy just from a single neutron. And that's the basic premise of how a nuclear reactor is able to make its power. So at this point, you're probably wondering, why thorium specifically? I mean, like, yeah, I mentioned how it's better, but what's so good about thorium in specific? Well, if you take a look at these pie charts here, you notice that there's a lot more thorium than uranium in the world. Thorium is actually about 3 times more common than uranium, not to mention that all thorium, well, not all, but a significant amount of thorium, enough to make the rest negligible, can be made to work in a nuclear reactor. However, only about 0.1% of uranium can be. And that's actually becomes a problem later when the rest of the uranium gets to turn into nuclear weapons. So, as you can see, uranium is fertile and thorium is fertile. What does that exactly mean? Well, it means that you can, in theory, make that uranium or that thorium be able to work in a nuclear power plant. You can see that only that 0.1%, that green sliver there, is fissionable. And that means it will work in a nuclear power plant. And you might be wondering, okay, well, fertile, fissionable, what's the difference? Well, fertile can become fissionable if under the right conditions, generally when other fission is occurring around it. So as you can see, thorium is not only more abundant, it also can be used in nuclear reactors. It's cheaper and more economically viable. So to get into the specifics about how thorium is actually used in a nuclear reactor, to be clear, uranium is the only thing that can really do fission in a nuclear reactor. I mean, every single nuclear reactor we've ever made, it uses uranium in some way. So you might be wondering, why are we using thorium then? It's not uranium. Well, as I said earlier, it can be made fissile because it's fertile. If you give thorium a neutron, it'll undergo a series of beta decays until it reaches uranium-233, which is a very fertile isotope of uranium that can be used in nuclear reactions. So to go more into the specifics about why we're going to be switching materials here, we also want to talk about the water problem. Water boils at a very low temperature, which might come to a surprise. If you ever put your hand in a pot of boiling water, you're not going to have fun. But in the realm of nuclear reactors, where temperatures can reach 1,000 degrees centigrade, the boiling point of water is pretty low. So if anything comes in contact with anything, it's going to boil unless it's under extreme pressure, which is why inside of a reactor you have to pressurize everything to a point that increases danger and the cost of making the whole thing run. So thorium reactors were actually able to solve this problem using salt. That might sound a bit weird. I mean, how is table salt going to work in a nuclear reactor? Well, the term salt actually refers to any ionic compound. You might learn that from chemistry class. And in this case, the specific salt we're using is thorium tetrafluoride. You can see the rough drawing of it right here. And the benefit of thorium tetrafluoride is that when you mix it with fluorine, lithium, and beryllium, it creates a substance the nuclear reactors are not only able to use as their fuel, but also something that doesn't turn into a gas when you only heat it up slightly. So salt is our go-to option for creating thorium reactors. Another added benefit of salts is that since the fuel itself is a liquid, you can actually pump it in and out of the reactor, which means that you can treat that fuel, you can remove impurities, you can add more thorium, and it allows you to keep up your runtime at 100% by adding fuel just while you're running. You can have access pipes, like shown in the diagram, to add more fuel as you go. So you essentially never need to stop these things. And then the final key in this puzzle is that of safety. Thorium reactors don't explode, period. They're the safest form of energy that humanity has ever conceived of. And the reason that they're so safe is because you're able to pump out the fuel in the case of an emergency. So not only is there no water, which reduces the chance of random things exploding, the fuel can be easily disarmed by turning on turbo pumps at the bottom of the reactor. In case you don't know what one of those turbo pumps is, it's something that can run without any power. So in the event of an emergency, all you need to do is press a button and crisis averted. There's no complex task that may or may not work. It's essentially guaranteed that you're not going to have any accident. Furthermore, should an accident occur, it's not going to be even nearly as bad as what happens with something with like Fukushima or Chernobyl. So that's in terms of the reactors, but safety isn't always in terms of what its direct use is for, but also what it's used otherwise. In this case, nuclear power gets a bad rap because it's also able to, well, create nuclear bombs, which I don't believe anybody really likes. So to understand why thorium reactors are safer in terms of nuclear proliferation is this pattern here of how plutonium is actually created. First, you take uranium-238 and you add a neutron. Keep in mind that thorium reactors don't actually have any uranium-238. So you can't actually create plutonium from the very first step. After that, it turns into uranium-239, and after a couple of beta decays, it turns into plutonium. So, not only is thorium power not going to explode in a reactor, it's also not going to make anything else explode, ever. And that comes up to the total of my video, and here are my works cited. I guess you can